Okay, in this problem, we are trying to calculate the magnitude of force between two 2.5 grams pennies separated by 100 meters, and we are told that each penny has lost 1% of its electrons compared to its protons. So we are trying to solve for the magnitude of the force, and we are given the distance, and the problem also mentions electrons and protons, so we're probably dealing with charges here, so we should use the Coulomb's law, which is magnitude of the force equals to Kc, the constant, and the magnitude of Q1 and magnitude of Q2 over d squared. Kc, the constant, is 9 times 10 to the 9th nm squared over c squared, Newton meter squared over Coulomb squared, and d is given to us in the problem, which is 100 meters. So we already found two variables, but how do we find Q1 and Q2? So in this problem, we are given electrons and protons, or we are at least told that protons and electrons have something to do with this problem. So in this problem, we are also told that these are pennies. So pennies are made of copper, and copper, protons, and electrons, we could easily find the number of protons by using chemistry, stoichiometry, Avogadro's number, molar mass, and the periodic table. So we are given 2.5 grams of copper in the problem, or 2.5 grams of pennies, but they're made of copper, so we could assume that they're just copper. And 1 mole of copper is 64 grams of copper. That's the molar mass. And 1 mole of copper is 6 times 10 to the 23rd atoms copper, which is the Avogadro's number. And in 1 atom of copper, there are 29 protons, which is the atomic number. And this would be our number of protons. And this would be equal to, from our calculator, it would be equal to 6.80 times 10 to the 23rd protons. Now, a charge of 1 proton in this case is equal to a charge of 1 electron, which is equal to 1.6 times 10 to the negative 19 coulombs. If our pennies were neutral, say it didn't lose any electrons, then these two would cancel out by its net charge. So QP minus QE, it would equal 0. But because we lost 1% of our electrons, it's not 0 anymore. So QP is the number of protons, and this is E, by the way, times E. So the number of protons times its charge, and this is QE equals the negative number of electrons times E. Now, our number of electrons has lost 0.01, or 1% of its original amount of electrons. So we write it like this, or any nu. But we can also write it as number of protons minus 0.01 number of proton, because, well, they're the same thing. Like, this is like from, if said it was like neutral, they would be the same thing, same number amount. And we want to write it like this because if we were to write the QNet equation and plug QP NP times E minus this new NE, which is NP minus 0.01 NP times E, don't forget, we would get, well, if we were to distribute this, this would cancel out, and we would be left with a 0.01 NPE. It's a little messy, but if you were to do the problem, then they would cancel out. And that would be our Q net. And this would also be our Q penny with that loss of electrons. And now we can actually plug it into our Coulomb law equation. Well, I'm going to actually plug it in. Kc is 9 times 10 to the 9th nm squared over Coulomb squared. And this would be 0.01 times, we already found out the number up here for NP, times E, which is 1.6 times 10 to the negative 19 C squared, since both Q1 and Q2 in this problem are the exact same. And D squared, that's 100 meters squared. And if we were to plug it into our calculator, it would be 1.07 times 10 to the 12. And check our units, m squared crossed out, c squared crossed out. We're left with newtons, and that's our magnitude of force.